Thank you, Brandon. There was some really interesting points that he had on improving the efficiency of cars. Next, I'll bring to you Nathan Berkowitz, and he'll be giving you an introduction on the experiment of the clapeyron.
How y'all doing? My name is Nathan Berkowitz, and like Marcus said, I'm going to be presenting to y'all on the experiment that a couple of our groups will be doing next week, the clapeyron experiment. To give you a little bit of introduction as to what the clapeyron equation is, it's a equation that relates a lot of important thermodynamic measurements, and it's very useful whenever there's a change in a substance that can't be easily measured. In our case, we're going to be dealing with the enthalpy of water. We're going to be taking different pressure measurements at different temperatures throughout the experiment, and with those readings, we'll be able to easily calculate our enthalpies. A little bit of background on clapeyron. He's most known for expanding on existing work, such as Carnot's work. He was able to take his work and put it in a lot more analytical and graphical form so we could understand it a lot better. He also further developed his reversible cycle, which was first introduced by Carnot, which we now know as the second law of thermodynamics. With these as his background, he was able to expand on Clausius and develop the clapeyron equation that we'll be using in the lab. Some important things that we need to remember from thermodynamics is the saturation pressure, which is the pressure at a corresponding temperature whenever a liquid begins to boil. The latent heat of vaporization, which is the heat that is required to change from liquid to a gas. The specific volume, which relates the volume of a substance and its mass. Entropy, which is the flow of heat, and the ideal gas law is used as a simplification in the clapeyron equation. The objectives for this lab is we're going to determine the latent heat of vaporization of water, and then once we find those latent heats, we're going to compare them with the tabulated values in steam tables. The clapeyron equation, as I said, relates the change in saturation pressures over the change in temperatures, and gives you the enthalpies over the temperatures and the specific volumes. And you can use the ideal gas law as an approximation whenever the vapor phase is present at low temperatures and the saturation pressure is relatively low. The apparatus that we'll use for this experiment is exampled by this schematic. You have the beaker, and you have a heating plate, which is going to boil the water inside the beaker. You have the thermocoupler, which is going to be taking the readings, the pressure transducer, analog pressure transducer, the analog readout gauge for pressure, a air bleed valve, the vacuum control valve, the centrifugal pump, a water reservoir, and a computer that runs the data acquisition software. For the procedure, you've got to make sure that the computer is operating the data acquisition system. We need to find out from Solomon or Mark if we're going to be using the boiling beads. Those are used to prevent flash boiling, which is very dangerous and can cause damage to the equipment, can ruin the experiment, and can also burn the people around it very badly. They provide nucleation sites on the for the water to kind of boil, so it makes it a smoother boil, and you don't have that flash boiling effect. Then set up the rest of the apparatus as shown in this schematic. We're going to create a vacuum in that flask, and then once the vacuum is reached, or as close to the vacuum as we can get, we're going to start the water to boil and begin logging data once it reaches a boil. As soon as the water has reached boil and we start logging the data, we're going to slowly close off the vacuum line and allow the pressure to increase to atmospheric pressure. And once it has reached that, we're going to stop recording the data. This is a plot for set the pressure versus temperature. I use the values in the back of the thermo book to create this chart. For the calculations, I had to tabulate the latent heat of vaporization for 3 random pressures. Simple algebraic rearranging solved for the latent heat of vaporization using the ideal gas law as an approximation. This is the value that I calculated for my first pressure, and the actual value that was found in the back of the book. For my 3 pressures, that's what I got, and those were the actual values. I think the reason why my values were off from those is because of my slope of my tangent lines were a little off. So that's what. Any questions? Thank you. Okay.
So what are the possible sources of error in my experiment?
Possible sources of error would include, I guess, where the thermocoupler is located in the beaker. If it's too low and touching the bottom of the glass, it could cause errors in the temperature. You wouldn't be actually recording the temperature of the water. That's like one of the major sources of error, I guess. Or if the software is not acting correctly and you're taking your readings off, that could cause sources of error as well.
Then your plot, you said the plot was slightly different from
Oh, my values?
Right. So because of your gradient. So you thought you have done a good job in taking a better gradient?
Yeah. For that, it was supposed to be, it's the slope of the tangent line at those pressures, and I think my slopes were inaccurate, so I think that's why my values were off by that much.
Did you try like a couple of slopes, I mean gradients?
Yeah, I tried, and that's the closest that I could get, so tried a couple different, that was the closest values that I could come to. Any other questions?